Hello, everyone. So I'm really happy to announce the next speaker. He's Matías Pavez-Signé from University of Chile, and he's going to talk about the extendability method in sparse expanders.
Okay, is this working? Okay, good. So thanks, Pedro, for the introduction. Also, thanks, Rob. Okay, he's not here yet. But thanks also, Guilherme, for the invitation. It's very nice to be here because I'm also giving this talk because it's kind of closing a cycle in some way. So I first learned about this method around 7 years ago here while working with Pedro and Luis. So it's very nice to talk about this 7 years later. Oh, it's crazy. Okay, so what is the extendability method? So this was first introduced by Friedman and Pippenger in 1987 to show, among other things, that the size Ramsey number of bounded degree trees is linear in the number of vertices. And since then, it has been used in many, many different contexts. Just to mention some, we can solve with these Turan problems in GMP, Ramsey problems in GMP. It was used for the amazing proof of Richard Montgomery of the universality of bounded degree trees in GMP. Also for the two universality in GMP. Recently, it was used for the solution of the Hamiltonicity problem in pseudo-random graphs. And also it has been used in Dirac type problems in random and pseudo-random graphs. So my idea today is to, of course, introduce this method and show two very recent applications. Okay, so the only definitions I think we need are the following. So suppose we have a graph G, and we have a subset S of vertices. So the first thing we appears there, gamma of S, is the neighborhood of S, just the collection of all vertices we are neighbors of S. And the second thing here, N of S, is the external neighborhood. So is the set of those vertices outside S having neighbors in S. Okay, so what is an expander? There are many, many, many ways to define an expander, but this is possibly the easiest way. So we say a graph G is a DM expander if every time I pick a set S, which is small, it has size at most M, the size of the external neighborhood expand by a ratio of D. So we pick here S, we look at the neighbors outside, and the size of this neighborhood is going to grow by a factor of D. So we have to think of it of this like S expand by a ratio of D. Sometimes, in this talk, D is going to be a constant, but sometimes it could be something which goes to 0. Okay, so the second definition is a graph being M-joined. By this, I mean that if I pick two sets, A and B, both of size M, I always see an edge in between. Okay, so these two definitions might be, maybe you don't see the relationship between these two things, but this is equivalent to say that if we pick a set of size at least M, the external neighborhood is going to be very, very large. And actually, you can do even better. We can prove that these two definitions are actually very, very related. So if you have a graph G which is M-joined, and we have some condition on the size of G's, so it's at least, let's say, 100 times D times M, then we can find a subgraph which is going to be very, very close. We're going to have size very close to G. So we only miss at most M minus 1 vertices. And this graph G prime is going to be M-joined because G was M-joined. But also it's a DM expander. So if we have a graph which is M-joined, we can remove a very tiny fraction of the vertices. And the graph is going to be M-joined, but also expander. So these two properties are kind of very well related. Okay, everything good with these two definitions? It's going to be essential for the rest of the talk. Okay. Okay, so examples about expanders and M-joined graphs. So the first example is obviously the random graph. So if you have a random graph with P of the form 1 over N, then with high probability, it's going to be M-joined for M of the form log MP over P. So in particular, if we pick P of the form C over N, then for any epsilon, we can choose this constant C large enough. So GMP is going to be with high probability epsilon N joined. So every time we pick in GMP sets of size epsilon N, we always gonna see an edge crossing. But if we pick p larger, let's say at least log n over n, or much larger than log n over n, we will have like a sublinear jointness. So every time we pick sets of size n times log n over log n, we're going to see an edge crossing. Good. The second example are the so-called pseudo-random graphs, which are graphs which are deterministic in nature, but share some properties with the random graph. In general, the property we're interested in is the edge distribution. So we want the edges to be evenly distributed among the vertices of the graph. So this definition was proposed by Nogalon in the 90s, which comes from spectral graph theory. So we say a graph G is an ND lambda graph if three properties hold. First, G has n vertices. Second, G is d-regular, so every vertex has d neighbors. And the last condition is the difficult one. So it says that all non-trivial eigenvalues of the adjacency metric of G are bounded in absolute value by lambda. So this last definition could be a bit weird, but we will see in a moment how to use this condition here. And an example of ND lambda graphs are random d-regular graphs. So random d-regular graphs are ND lambda graphs for D of the form root D. So this is what we call an optimal ND lambda graph. So this is the best thing you can hope for in an ND lambda graph. Okay, so why this definition makes sense? Why is this a good definition for a pseudo-random graph? Why is this a pseudo-random graph? This all comes from the so-called expander mixing lemma, which says that if we have a graph, an ND lambda graph G, then every time I pick any set of vertices A and B, the edges between A and B are some or less are essentially the same as in the expected the expected value of crossing edges in the random case where P is of the form D over N. And the difference between these two numbers is going to be controlled by this parameter lambda. So if lambda is very, very small, we're going to have more control on the distribution of edges across the graph. Okay, so from this lemma, we can deduce two things. First, if we have an ND lambda graph, then this graph is going to be lambda n over D joint. Good. And the second is going to be an expander. It's going to be D lambda n over D expander. So let's remind what it means. So every time we pick a set of size at most this number over here, the neighborhood, the external neighborhood, is going to expand by a ratio of capital D, this capital D. And this capital D is going to be of the form D over lambda. So this parameter D over lambda, which is also called the spectral gap, is going to be controlling how good is the expansion in this graph. So in this area, one of the fundamental questions is the following. So we have a graph H which has n vertices. And what we want is to find the weakest possible expansion conditions forcing that every ND lambda graph will contain a copy of H. So the question is, how large does this spectral gap, D over lambda, need to be so that if G is an ND lambda graph, then we can find a copy of H in G? So that's the fundamental question in this area. In random graphs, we want to find the threshold. In expander graphs or pseudo-random graphs, we want to control the expansion, or how good is the pseudo-randomness so that it forces that H is contained in G. Okay, so to give a brief overview on this extendability method. So this is the main tool that we use to try to solve this question. So this, as I said, the extendability method was introduced by Friedman and Pippenger in the 80s. And then it was improved by Penny Haxel in 2001. She essentially proved that if you have slightly better expansion conditions, you can bet larger things. And then De La Monica Jr. and Yoshi here, they prove an algorithmic version of this method. And I put these names in red because obviously this method wasn't called the extendability method. It was these people, Glebov, Johansen, and Krivulevich, who named this method in this way, and they define a new language to use this method, which is much more nicer, I would say. So Glebov, Johansen, and Krivulevich rename or rephrase this method in the extendability way that I will show later. But it wasn't appearing in a paper. Actually, this appeared in the PhD thesis of Glebov, and the first time this appears in a paper was in the paper by Richard Montgomery in the proof of the universality for bounded degree trees in GMP. And last year, Girao and Harley, they proved also an induced version of this method. So today, my plan is to introduce the extendability method as in Glebov, Johansen, and Krivulevich work, and show how this can be used to attack this kind of problems. So try to find spanning structure, a very large structure in pseudo-random graphs. OK, so just to remind the definition, if we have a graph G and we have a vertex subset X, this is the gamma of X is the neighborhood, gamma of X is the neighborhood, N of X is the external neighborhood, and the crucial definition of the method is the following. So let's try to go slowly here, because it's kind of technical. So we have two parameters, D and M. This is very similar to expansion, right? So M is going to control the size of the sets we want to control the neighborhood, and D is going to control the size of the expansion. So we're going to say H, a subgraph H in a graph G, is DM extendable if two things happen. First, the maximum degree of H is bounded by D. This might be arbitrary, but it is important. The second property is that we have expansion. So for any set X in G of size at most M, we have some control on the size of the neighborhood outside my graph H. So let me write a picture. So here we have G. Oops. So here we have H is anything. I pick X, which could intersect H. I look at the neighborhood. And what I want is that this part, which is the neighborhood outside H, is large. So this has to be at least D times size of X minus something. So essentially, we are saying sets expand, but outside H. And this factor over here is essentially counting how many neighbors we have inside H. So we want expansion outside H, and that's the idea. So if we have a graph so that small sets expand outside, we call this graph a DM extendable. So everything good with this definition is the most difficult, I think, definition in this talk, but it's very related to expansion. OK, so maybe this definition is a bit complicated. And if we want to use this extendability method, we really need to check if a graph is extendable. So
if the graph is D-regular, then this taking off this term is just saying you're ignoring all of the vertices in X, etc.
Yeah. Yeah. So they could overlap. Yeah, if they overlap, you have to count how many neighbors they have inside the graph. But if they don't overlap, we don't care. OK. So the first thing I would like to mention to you is how to check in a pseudo-random graph, let's say in an ND lambda graph, how to check extendability very easily. Because this could be hard in general. But if we have a graph which is extendable, we can apply this method to find many things. So let me first show you how to check extendability in a very broad way. So suppose we have a graph which is ND lambda. So what we typically do is to sample a random subset of linear size. So if we do that, we're going to preserve the minimum degree. Say the degree is D in the ND lambda graph. If we sample a P random subset, the degree is going to be roughly P times D. OK. In that case, one can show using the expander mixing lemma that every subset S is going to have a large neighborhood in this random subset R. So this is good because no matter what we embed here in red, this subgraph is going to be extendable. Why? Because you're going to have a large neighborhood in R, in this random subset. So in ND lambda graphs, in this world, if we pick a random subset and we do whatever we want outside, it's going to be extendable. So if yes, S is X in the previous.
What was H in the picture?
H is this red thing. Yeah. So let's say I embed this red thing. It could be a point, let's say. And this thing is going to be extendable just because it has good minimum degree in this random subset. So the expander mixing lemma implies, because the neighborhood expands. Sorry, small sets expand into this random subset just because of the minimum degree. You can do some double counting and it works. OK. So checking extendability is not hard by taking random subset. So this is the key lemma of the method. So let's go slowly because it's hard to read. So suppose the setting is we have a graph G, we have a subgraph H, which is DM extendable according to the previous definition. So every small set expand outside H. And suppose we have this expansion notion for larger sets. So extendability says we have expansion from small sets, for sets from size. So extendability says I can take any subset X of size between A1 and M. So if we have some additional condition like here, so here I'm saying if I take a set X of size between M and 2M, and it has a large neighborhood, then what I can do, for any vertex X, which has degree at most d-1, I can find a neighbor Y outside my graph and add this edge to the graph. It says, the lemma says, OK, if I add this edge xy, then this graph remains extendable. So we don't destroy this extendability property by adding this special edge. Is it clear? Any question? OK. So again, we have an extendable graph, H. We pick any vertex of degree at most d-1, X. This lemma says we can find a neighbor outside so that if we add this edge xy, the graph remains extendable. So what is the idea of this lemma? Well, what is this useful for? So this key lemma says, OK, if I have some expansion condition like this for slightly larger sets, I can do vertex by vertex embeddings in very sparse graphs. So in general, we should think that ND lambda graphs, so the D we are choosing in the ND lambda graphs is like constant. So we have a very small control on the degree. And even in that case, we can do vertex by vertex embeddings, which is amazing. We cannot choose the vertices, but we know there exists at least one neighbor outside which we can add. OK, so what if the graph is M-joined? So can we check this property easily? So suppose G has M vertices. Let me pick any subset X of size between M and 2M. Then we can check that the neighborhood, or maybe easier, the non-neighborhood of this set X is going to have size at most M-1. So the neighborhood is going to be at least N minus M-1. And we need this condition to hold. So if we want this condition to hold, the only thing we need is this red condition here. So essentially, this is saying that if we have an M-joined graph, we can embed graphs of size up to as long as they satisfy this condition here. So we can embed very, very, very large graphs just using this method. Yep.
I missed the first couple of minutes. Are you just trying to embed trees?
For the moment, yes. For the moment, yes. So this is the next slide. So for example, what we can do. Very good. So the first thing we can do here is to embed trees, very large trees. So this lemma is saying, OK, if I want to embed a tree, I can do a vertex by vertex embedding. And as long as the tree has maximum degree at most d, and it has at most n minus some constant times d times m, we can embed this tree easily, just using this method. So this method for free gives us very, very, very large trees. Okay, what else can we do? Can we do cycles? The answer is yes. We can also embed very, very long cycles. So we can embed cycles up to order n minus, again, d times n. And the idea is the following. So we can find a very long path using the extendability method. Then we can grow here, let's say a binary tree here, until the point here, the number of leaves is going to be m. So we have m leaves here, and we can find then an edge by the m-John property. So not only we can find trees, we can also find long cycles. So my plan for today is try to convince you that this method is very useful for finding, for example, Hamiltonian cycles in ND lambda graphs, and also for studying, if I have time, hopefully, to study Ramsey problems, in this case for bounded degree trees, but can also be used to study Ramsey goodness for cycles, for example. Okay, any question before I go to the next slide? Okay, good. Okay, so let me start by studying the Hamiltonicity of ND lambda graphs. So this was I say was because it was solved very recently. This was the central conjecture in pseudo-random graphs. What is the threshold, or what is the weakest possible condition we need to find a Hamilton cycle? So Krivulevich and Sudakov, 22 years ago, proved that if we have any ND lambda graph with a spectral ratio large, just a large constant, then this already forces the graph G to be Hamiltonian. Oops. Any guess why this should be the right answer? Not GMP, but D-regular graphs. D-regular graphs are already Hamiltonian for D equals 3, if I'm not wrong. So if this is a large enough constant, then maybe, possibly this should be true. I think that's the motivation behind this conjecture. OK, so what is known about this? Or what was known before the solution? So Krivulevich and Sudakov proved that if you have a spectral graph slightly below log n, then you can find Hamilton cycles. So they proved that if d over lambda is larger than log n times log n over log n, then this is enough. Nothing happened in like 20 years until Glock, Muñoz-Correia, and Sudakov. They showed the first improvement in like 20 years. They proved like, OK, log n over times log n over log n is good, but you can do log n to the power of 1 over 3. And well, they proved this, but they also proved another thing. They proved also that the conjecture holds if we add some condition on D. So they proved if this polynomial in N, this is the conjecture is true. And this was the motivation behind this work here. So Ferberhan, Jehan, Mao, and Bershin, they proved that if the degree here, D, is polylogarithmic, then the conjecture is true. But the same day on arXiv appeared this paper. So Draganich, Muñoz-Correia, Montgomery, Prokofsky, and Sudakov, they proved an even stronger statement. So this is not only true. They proved that the conjecture is not only true for ND lambda graphs, but we only need some weak expansion conditions. So they proved that sparse expanders are Hamiltonian. So let me try to. I would like to try to show you the solution of a sketch of the solution of this result. Okay, so one of the main ideas when we try to find Hamilton cycles is the following. So the first step is to find a very large linear forest, maybe covering almost every vertex, say. So here we have, let's say, T paths. They might have different length, I don't know. And the second step is try to connect the endpoints of this path, maybe using the leftover vertices, all the leftover vertices at the same time. So maybe what we want to do is to find paths like this in red to close this cycle into a, to close this path into a Hamilton cycle. So this is roughly an idea which is very useful in this setting. The problem is, OK, maybe the first step is easy, maybe using extendability or maybe using, for example, let's say Lovász local lemma. But the problem is the second part. The second part is in general quite hard. Sometimes we use a tool called the absorption method, which in the case of pseudo-random graphs, it doesn't give the right answer. So we don't know how to build efficient absorbers. So if you want to do absorption method, if you want to do absorption, the best thing you can do is of the order log n to the power 2, so log n squared. So this is not an option here. So let me show you the first, Let me show you the first step. So if you want to find a spanning linear for, let's say, so one strategy is to use a random partition. So we can pick a random partition, all the sets VIs of the same size, and then we can show in an ND lambda graph that with positive probability, each of these bipartite graphs, VI plus 1, will satisfy Hall's condition. Well, that's not what we do. We can show you that minimum degree condition essentially implies a Hall's condition. So what we can do is this bipartite graph, yeah? So this bipartite graph satisfies Hall's condition, so we can find a perfect matching. Then we can find another perfect matching here and so on. So this gives us a collection of short paths covering every vertex in the graph. The second problem, though, is quite difficult and actually has a name. This is the connecting path problem. And the problem is the following. So we have a collection of pairs, xi, yi, from 1 up to t. And what we want is to find a collection of paths connecting xi with yi. This is a well-known problem, has been studied in random graphs and also in ND lambda graphs by many groups of people. Let me show you how to solve this problem using the extendability method. Okay, as I show you, what we can do is to use the extendability method, find a path, then find this binary tree, and use the join property to connect the leaves, like this. The problem of this strategy is that it's very expensive. So every time we do this tree here, we are using lambda n over d vertices, because we want lambda n over d vertices here, lambda n over d vertices here, and then use this lambda n over d joinness to find this edge. So this strategy is very expensive because if we do this, we need these conditions to hold. We need that these t paths we are finding times the size of these trees, which is essentially lambda n over d. We need this to be at most the number of vertices in my graph. But this forces that t is at most d over lambda in order. And this could be a constant in the worst case. So this is saying in the worst case, this only allows us to find constantly many paths. So the amazing idea that happened like 15 years ago is that we can, is now called the rollback method, which was introduced by Daniel Johansen in the PhD thesis I told you about, where they named this thing as the DMX extendability method. So the idea is the following. So we have a graph H, which is DM extendable. We have a graph H. We don't know if this graph is DM extendable, but we know that there is a vertex Y such that if we add, let me write this thing. So here I have H. I have some vertex X, which has a neighbor outside, Y. And we know that X plus XY is DM extendable. So this lemma says that we can remove XY and the graph is extendable, which is obvious, actually, because we only care about neighbors outside the graph. So if we remove a leaf, the graph is going to continue to be extendable. So this observation is trivial, but I'm going to show you that it's very powerful. The second observation is that if I have, this is also, I think, is going to be important. So let me remove this. So suppose I have two vertices here, x and y, and this edge belongs to the graph, but not to H. So this edge belongs to G, but not to H. We don't know. The second observation is saying that we can add this edge, and everything remains extendable. Again, it's obvious, because we only care about neighbors outside the graph. But these two observations are quite powerful. Okay, these two observations allows us to connect vertices in a very efficient way. So suppose we have a graph which is M-join and expander. We can grow a DRE minus 1 tree of depth logarithmic, the same thing here, and then use the M-join condition to find this edge here. So this edge gives us a path, like this. And we can use the first observation to remove all the remaining vertices. So we can remove, oops. We can remove all these vertices here, except those in the path, and everything is going to remain extendable. So now we are not using linearly many vertices to find one path. We're just using logarithmic many. And everything remains extendable. So if we do this, we can repeat this argument up to n over log m times. So we're now able to connect n over log n times a path, and not constantly many as in the previous attempt. So this is kind of weird, because these two observations are kind of, I don't know, straightforward, but it took us 20-something years to realize this. Yeah?
So you found these paths, and then it seems like you're doing exactly the same thing you did before, so I don't understand why this is suddenly better.
Slightly, but not this. OK, so we have x1 up to xt, y1 up to yt.
That was all the vertices.
And almost all the vertices. Let's say n minus 100 mu n for some small mu. OK, I find this path. I find this path. I do this, I find this edge. And this is my first path.
Extra ones you're using are now taken from the other path?
No. OK, let's say we don't have this. I'm just growing this binary tree here. OK, I'm just using, let's say, mu n vertices to find this thing.
You're using the ones that you have that are outside?
Yes. So we have some left over here, 100 mu n leftover vertices.
That's big enough for you to find this thing?
Yeah. So now I'm using this M-join property to find this edge. And now I can delete everything here. I keep only the path, and everything remains extendable.
Because you're using it this same trash set that you're back in the trash.
Yes, exactly. And then I can repeat. And I'm just using logarithmic many vertices at each step.
Yeah, the body just has to be small enough that
Yeah,
it's in the trash.
exactly. Thanks. So this is way more efficient than the previous attempt. Because in the previous attempt, we can only connect constantly many vertices, pairs, sorry. In this case, we can go up to n over log n.
The previous time was just the difference was you're doing all at the same time.
At the same time, yeah. OK. So to close this idea, this is saying in the case of ND lambda graphs that, OK, recall in an ND lambda graph is going to be M joined for M lambda n over d, and it's going to be an expander with ratio d over lambda. And this is saying that if you have any pair of points, we can connect those points with a path of length, essentially log n over log the expansion ratio. Let me also observe that this is tight. This is tight by a construction of very famous construction of Lubotsky, Phillips, and Sarnak, showing that there are ND lambda graphs with logarithmic girth. So you cannot do better than this. OK, so let me go back to the Hamiltonicity problem. OK, so we can find this family, very large family of paths using, let's say, this trick of the matchings. So the problem is when we expose these matchings, we don't know which pairs are connected. So I'm connecting this vertex with some vertex here, but I don't know beforehand which is going to be the pair. So this is a problem here. So what we do to solve this problem, we propose a new approach which solves the connecting path problem in a robust way. What it means that I give you the collection of points, x1 up to xt, and also y1 up to yt. I don't specify which pairs I want to connect. What I want is that for any bijection from t to theta, so I give you any possible way to connect this point with this point, I would like to solve the path connecting problem. So I would like to find a collection of paths vertex disjoint, so that each path pi connects this guy, xi, with y under the image of this permutation here. So I want to connect in all possible ways. I want to solve this path connecting problem in all possible ways. This is the difference. Let me show you how we do this. So as a warm-up, let me show you for two vertices. So I have x1, x2, and y1, y2. What we can do is to use a cycle of length 4, or k to 2. So we can find a path, go through this cycle, to produce two types of paths. So the first one is to connect x1 with y1 going in a straight line, and x2 to y2 in a straight line. But we can also do the following. I can go to this path, cross, and then go to y2. And also the same thing here. x2, use this edge, and go to y1, sorry. So this is just for two vertices, or two pairs. So if we have more vertices, we need something more complicated. So these are all the connections we need to produce all possible combinations of paths, these C4s. But the problem is if you have many different vertices, how we solve this problem? So we have two obstacles here. So the first one is that C4 doesn't appear in an empty lambda graph, typically, because the girth is logarithmic, could be logarithmic. So we need some gadget to replace this C4. And the second obstacle is that we need to allocate this gadget in some efficient way. To solve the first problem, we found this very magical gadget, which is just a cycle. So these straight lines form a cycle. And these wiggle lines are paths. And the idea is that you can do the same thing as in the C4 case. So I can either go a straight line and a straight line, or I can do the following. I can follow the red path to go from x1 to y2, which is not there. Or I can do the blue path to go from x2 to y1. So this thing replaces the C4. And this thing can be found in an expander graph, because I start with a cycle, let's say of any length. Let's say it's logarithmic, which is this straight line. And then I can find this path using the extendability method. So this thing can be found using the extendability method. And for the second obstacle, we use a very famous construction of archetype commonness and semiready for sorting networks. So this result, we use this result as a template to allocate these gadgets. And what we prove is the following. So we prove this with Joseph Hyde, Tash Morrison, Alt-Muyeser. We prove that if we have an m-vertex graph which is m-joined, we have two set of vertices. Let me write a picture. So we have here x. Here we have y. So we want to connect vertices from x to y. And suppose this graph consisting of the vertices of x and y is extendable. So what it says, we can find a subgraph S, so we can find containing x and y. So we can find, I call it this W. So we can find some subgraph S, and let's say the vertex set of this subgraph is x union y union W. So that if I give you any, sorry, first thing, the size of this graph is log n cubed times the size of x. It's extendable, and it solves the connecting path problem. So what is this? What is this precisely? That if I give you any bijection from x to y, so I give you any ordering in which I want these pairs to be connected, we can find a family of paths here which have the same length and uses all vertices here in W. So we can find a PL factor following this bijection phi. Okay, is this somehow clear?
What is I of X union Y?
I of X union Y is the graph with no edges, with vertex X union Y. So we want the graph to expand outside X and Y, so that we can find this path using the extendability. Okay, so how this approach can be used to prove the Hamiltonicity problem for ND lambda graphs. So this is the proof of Draganich, Muñoz-Correia, Montgomery, Prukowski, and Sudakov. So they first used this lemma to find this sorting network. Secondly, they find a spanning linear forest, F, so that all the endpoints of the spanning linear forest is completely contained in X union Y. And finally, they can use the sorting network property to close this cycle. So no matter what is the order I have to close these cycles, I know this can be solved, because this is the property of the sorting network. Obviously, I'm cheating a little bit here, because this part, the second step here, is quite difficult. So for that, they introduce a new idea, a new version of the Poisson rotation extension. Instead of working on a longest path, they were working in a spanning linear forest. So they introduce a new type of rotation for solving this problem. So this second step is quite difficult. But this is kind of a sketch of the proof. Okay, so any question before I go to, I'm going to change completely the. Sorry. Yes, we have to.
Otherwise, it just joins up arbitrary pairs.
Yes, I don't want to use any vertex inside this blue blob, because this is going to help us to finish the embedding. So I find a spanning linear forest outside this graph. The crucial part is all the endpoints are in X and Y, and then we can use the sorting network to connect them as we want. For any possible way we want to connect them, we can do it.
It's not a problem if you start with this any lambda graph and you can remove some huge chunk of the vertices, but nevertheless they can do this.
Exactly. This is a very powerful.
Isolated vertices.
Sorry?
I mean, for Aurora there might be isolated vertices.
Yeah.
Isn't this the same problem, finding this spanning linear forest outside and finding this connection? Isn't this the same problem? But how this helps?
How this help? Which?
You're also finding connections to this outside, right?
No, we are not finding any connections outside.
Is a spanning linear forest?
It's outside, but it uses X and Y. So, but X and Y are only allowed to be used as endpoints. So that's the difficult. It's very difficult, actually.
I forgot, what's the size of X? The square, the rectangle?
So you can think that X union, this part is going to have linear size, but very small. All this part, X union Y union this blue part in the middle, is going to have linear size, but very small. Let's say n over a million.
Is it chosen somehow? I mean, it can't be arbitrary.
Oh.
Because then you won't be able to find this spanning linear forest.
So what do you mean by arbitrary? Which part?
I mean, so your degrees are like constant.
No, it has to be large enough.
No, but I mean, you might have a vertex outside and all its neighbors are inside this little square.
Right. So we start by picking random subsets, so that doesn't occur. Yeah. So you can avoid that kind of thing by taking random subsets. So you have degrees wherever you want. Okay. So let me show you an open problem here, because actually this was the original motivation of us to where we introduced this technique. Okay. So now we know the Hamiltonicity problem is solved. I could say, at least to me, the next step would be try to find spanning trees. So this was conjectured by Alon, Krivlevich, and Sudakov in 2007. So they conjectured that the same threshold for Hamiltonicity is also true in this case. So for any bound delta on the maximum degree of the tree, there exists some constant C, so that if G is an empty lambda graph with a spectral gap at least C, then G will contain all spanning trees with the maximum degree at most delta. And this is I think, is quite hard, because in particular, it would imply that random D-regular graphs are universal for spanning trees of maximum degree at most delta. So this is, I think, this might be very, very difficult. But and this conjecture is wide open. So okay, I have like 10 more minutes or 15 more minutes around that. So I would like to show you another application of this extendability method, but now in Ramsey theory. Okay, so let me completely change of topic. So I'm going to talk how this extendability method can be used to find optimal bounds for the Ramsey goodness problem. So I hope everybody here knows about Ramsey numbers. So the Ramsey goodness name was coined by Burr and Erdős in the 80s. And it's defined as follows. So we have a graph G which is connected, and a graph H which is any graph. We say this pair GH is Ramsey good if the Ramsey number of G versus H satisfy this condition here. So it's exactly the size of G minus 1 times chromatic number of H minus 1 plus some parameter here, depending only of H, which is the size of the smallest color class across all proper vertex coloring of the vertices of H with exactly chromatic number of H colors. Okay, this doesn't really, I mean, if you didn't understand this, possibly this picture is going to explain it. So this comes from a very familiar construction. So suppose we have a graph G with m vertices. So this lower bound comes from a very natural construction, which you might know. So we have a chromatic number of H minus 1 blobs, each of size m minus 1, and a very small blob of size sigma H minus 1. So we color everything inside each blob in red and all crossing edges in blue. In this coloring, we cannot find any copy of G because G is connected. The connected components here in red have size at most n minus 1. So it doesn't fit. We cannot find a copy of H in blue because if we are able to find a copy of H in blue, then essentially we are finding a proper vertex coloring of H where the smallest color class has size at most sigma H minus 1. And this contradicts the definition of sigma. So this is a very natural lower bound. And Burr and Erdős were interested in trying to find or classify all the pairs G and H, which are Ramsey good. So in this talk, I'm just going to talk about trees. The conclusion is trees are Ramsey good. So the first result was actually before Burr and Erdős coined this name by Schwatal in the 70s. So Schwatal proved that any tree versus any clique is Ramsey good. And the proof is a very nice exercise. I really recommend to look at it. And then years after, Erdős, Faudrier, Rousseau, and Chelp proved that if you want to go from cliques to an arbitrary graph, you really need to put at some condition on the maximum degree. So they proved that for bounded degree trees, so if you have any bound on the maximum degree and H is arbitrary, the pair TH is going to be Ramsey good, provided that the size of T is large enough, depending on H and also on the maximum degree. And the dependency between the maximum degree cannot be dropped. So we really need bounded maximum degree here. So from this proof, it's not written in the proof, but you can deduce that you can take this constant to be size of H to the power of 4. And Bala, Prokofsky, and Sudakov were interested in trying to get optimal bounds for this number here. So what they prove is that you can actually reduce this number dramatically. So they prove that if you fix the bound on the maximum degree and k, if H is a graph with chromatic number k, then T is going to be Ramsey good with respect to H as long as the size of T is at least some constant depending only on delta and k times the size of H times some logarithmic factor. And they prove that or maybe they conjecture that you can remove this log factor. And OK, so what we did with Richard Montgomery and Jun Jan, which is a PhD student from Warwick, we proved that this conjecture is true. We proved that for any delta, any k, if you're given any graph H with chromatic number k, if n is large enough, depending on the size of H, then any n vertex tree with maximum degree maximum degree at most delta is going to be Ramsey good with respect to H. So we could remove this extra log factor in the previous result. And two things I would like to say here is this result is tied up to the value of this constant. And the best lower bound we could get is of this form. So we don't know if this is tight or not. So I don't have too much time, but let me try to convince you that this is related to expansion. So let me first talk about the case k equals 2. So in this case, let me assume the graph H is a complete bipartite graph. OK, so I'm given a complete graph on capital N vertices where capital N is n minus 1 plus m1. And let G be the red graph. So if the blue graph contains no copy of k, m1, m2, this is equivalent to say that the complement of G is k, m1, m2 free. And this is the same as saying that between in G, any set of size m1 and m2 have edge crossing if they are disjoint. So this is the same property essentially that we said before of m join, but now we have some unbalancedness between the sets. We call this property m1, m2 jointness. For larger k, you can do something similar. You can, doing induction on k, you can prove that you always have some expansion property. So you can prove this property in red here, that every set of size mk, every set of size mk is going to have a large neighborhood. And the proof is that if you don't have this property, then you can remove S and also the neighborhood. And you can go to the case k minus 1. So you can compute the sizes. You can remove the S and the neighborhood, call this graph G prime. The size of G prime is going to be at least the case k minus 2. And you can show that this graph either has a copy of this thing, or otherwise a G prime complement is going to be k m1 dot 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 mk minus 1 free. And then you can apply the inductive hypothesis. So naturally, this problem has some expansion condition going on in the underlying graph. So I don't think if I have time to say some few words about the proof. 5 minutes, OK. OK, let me say a few words about the proof. So let's say for k equals 2. And so in this case, suppose m1 is equal to m2 and is equal to mu n. We have a graph G with m minus 1 plus mu n vertices. By assumption, say the graph G is mu n join. So this is essentially the same as saying that the blue graph contains no copy of k mu n mu n. So the obstacle we have here to apply the extendability method is that it only gives us trees of size of G minus something which depends on the maximum degree of the tree, and also on the m coming from the joint condition, so which in this case is mu n. So we can embed trees up to this size, but we only have mu n minus 1 vertices, so this should be a minus 1. And the very nice idea is that if you take a random subset, you can shrink the size of the non-neighborhood by some constant factor. So this is saying essentially, if you take a random subset, you can shrink the size of the non-neighborhood. Instead of having mu n join, now we can reduce one of these parameters by some factor k, as small as we want. I don't want to show you the proof, but it's just a first moment calculation. Good. So this is the conclusion. We take a Q random subset with Q of this form, C times mu. X is the random subset. It's going to have size roughly C times mu n. The conclusion is that the induced graph by this subset X is going to be mu n over k joined. And Okay, so this is essentially saying we can reduce this parameter by any factor we want. What we can do next is to take another random subset. So here we have G. We pick X randomly. Then we pick X prime randomly. Now in X, you can prove that with positive probability, the induced graph by X prime is going to be mu n over K joined. So if you want to embed T, what we do is to, okay, first embed a big chunk of the tree here, covering every vertex outside X prime, and then use extendability to embed the rest of the graph. And the key part here is that we gain this extra factor over K, 1 over K in the extendability method. And now we can embed trees of size what is left over. This is X, it should be X prime. Size of X prime minus the thing coming from the maximum degree, but now with mu n over K. And the thing is, we have mu n vertices, and we embed things up to size of X minus mu n over 10. So we are gaining these things. So essentially, at the end, we just apply the classical extendability method here. But the difficult part is how to cover every vertex here. This is very difficult. So there are some obstacles here. I'm not going to show you, but in general, you have to do what is called a vortex. If you know about the iterative absorption, it's very similar. So you cannot apply the previous idea in general. You have to go through many steps to be able to apply this first moment calculation. And to finish, let me finish with an open problem. So I mentioned this in the open problem session, but many of the students weren't there. So 15 years ago, Allen, Brightwell, and Skokan made this very beautiful conjecture that paths are Ramsey good as long as the size of the length of the path is at least chromatic number of h times h, the size of h. Prokofsky and Sudakov proved this conjecture for graphs with chromatic number at least 4. So this conjecture is actually they proved that this conjecture in a strong form for graphs with chromatic number at least 4. But there was a very nice paper last year showing that in some cases you can do nearly 2 here. You can maybe put nearly 2 here. So my question is this true if you replace this 4 by a 2? Maybe this might be true. You can ask Luis and Fabio if it's true. Okay, I would like to stop here. Thanks.